Welcome back to Soils 404-504. The title of our course is Water Quality in the Pacific Northwest. Today we're going to continue to look at groundwater quality. Last time I introduced some concepts associated with groundwater quality, and in the next two lectures I wanted to pick probably the most common contaminant in groundwater, which is nitrates, and talk a little bit more specifically about nitrates. When you do your mini projects with groundwater, you can select a contaminant if you'd like to talk about it. So I'm going to give you the history and the background of nitrates and how it relates here in the Pacific Northwest. So here we are with nitrates. Nitrates are a very common contaminant when a person talks about water quality, groundwater quality specifically. Nitrates is usually the first contaminant to arise in a conversation. And that's because nitrates come from lots of different things. Probably most commonly, nitrates are associated with commercial nitrogen fertilizers. Nitrogen fertilizers are manufactured, or the vast majority of nitrogen fertilizers used in the world are manufactured using a process called the Haber-Bosch process, from where nitrogen gas in the atmosphere is captured by a catalyst and forms ammonium. Ammonium is a form of commercial nitrogen. About 95% of all the commercial nitrogen sold in the world is ammonium. When ammonium is put into soils, in the presence of oxygen and certain microbes, nitrifying bacteria, ammonium changes to nitrate. If you take a look at these two forms of nitrogen, ammonium and nitrate, both of them are plant available forms. They're equally good for plant use. However, the properties of these two forms of nitrogen are quite different. Ammonium has a plus charge. Soil particles and organic matter have a negative charge. Consequently, ammonium is attracted to soil particles. And this is a good thing because ammonium is less prone to leach in soils. However, once microbes convert ammonium to nitrate, nitrate has a negative charge. There's really no positive charges in soils to attach to nitrate. So nitrate sits in the soil water and moves with the soil water. If we have too much rainfall or we over-irrigate something, that nitrate moves with the water, and most of the time it moves downward, and lots of times this can result in contamination of groundwater. Besides commercial fertilizers, there's a lot of other sources of ammonium and then nitrate in soils. Our soils in the western United States contain anywhere from 1.5% to 3% organic matter. And organic matter is just broken down or plant and animal residues that are in different stages of decay. When the plants and animals die, they are broken down by microbes. We call it the process of mineralization. And mineralization is basically a two-step process. It consists of, the first process is what we call ammonization. Ammonization is where our dead plant and animal bodies, which we'll call proteins, are broken down from long chain molecules into simple chain molecules. An example here would be a carbon-based compound that has an NH2 attached to it. Byproducts are carbon dioxide and energy. So our dead plant and animal materials are broken down from long chain molecules, carbon molecules, to short chain molecules. That's ammonization. And in the second step of the process, those short chain molecules undergo a process called ammonification. And with ammonification, here we have our short chain carbon molecule that contains some NH2. In the presence of water, that NH2 is broken down into just NH2. and another carbon compound that will be further broken down, and energy. In the presence of water, that NH2, we add water to it, and we get ammonium. Ammonium, the same form of nitrogen that we get from commercial nitrogen fertilizers. So natural residues that break down in the soil are mineralized to ammonium, just like the commercial nitrogen fertilizers we use. Chemically, there's no difference between commercial nitrogen fertilizers and organic fertilizers, or natural products as we would call them. So we get ammonium, and then that ammonium can undergo nitrification, which is simply the conversion of ammonium to nitrate. It's a two-step process. We go ammonium to nitrite to nitrate. And again, we end up with nitrate, which has a negative charge. And because it has a negative charge, it can leach in soils. And we basically end up with leaching. So that's another form or a way that nitrates can get into our groundwater. Things get even more complicated because people that live in the country aren't connected to sewers. They have their own individual wastewater treatment plants. They have what's called a septic system. And we'll talk about septic systems later on in the course. Septic systems are basically waste treatment devices. Our liquid wastes come out of our homes and they flow into a septic tank. That septic tank holds large organic materials. Every 3 or 4 years, we pump out our septic tank to get rid of those large materials. But if people don't maintain their septic systems, they fill up. The septic tanks fill up, they can leak, and they can leak nitrate into the environment. And if nitrate gets into the environment, eventually it can end up in our groundwater. Another way nitrate gets into our system is animal waste. Any waste that animals generate, it's organic material, it's a carbon chain molecule. This carbon chain molecule undergoes mineralization by the microbes in the soil, and we eventually end up with nitrate, and that nitrate can leach. Another way nitrates get into our environment, we have plants that are called legumes, and legumes are famous for being able to fix their own nitrogen. They can grab nitrogen from the atmosphere, incorporate it in their plant bodies, and they use it for growth. We have a lot of legumes. A lot of land in the western United States is planted in legumes. Things like alfalfa, clovers, lespedeza, beans, peas, lentils. We actually have probably close to 3 million acres of alfalfa planted in the Pacific Northwest. And finally, we can get some nitrogen added to soils from the atmosphere. Traditional things like lightning discharges, fallout from acid rainfall. All of these things add a little bit of nitrogen to our soil environment. And again, this nitrogen, after it goes through a breakdown process or a mineralization process, can end up as nitrate, which is mobile in soils, moves with the water, and can end up in groundwater. So there's lots of sources of nitrates, and actually it's pretty difficult to keep nitrates out of groundwater in many areas. I have a publication that I would like you to take a look at. It's kind of old right now, but the data is relevant. It's called Idaho's 33 Nitrate Areas of Concern. It's a University of Idaho publication. It's Current Information Series number 1099. And I was one of the co-authors on this publication. We have, depending on how you count them today, somewhere between 25 and 33 geographic areas in the state where we have aquifers that have elevated levels of nitrates in them. And when I say elevated levels of nitrates, we're talking about human activities that have increased the nitrate levels in the groundwater. The states of Oregon, the states of Washington, lots of states in the United States have similar issues where they have aquifers that have what we would call elevated levels of nitrates in them. When I say elevated levels, we're talking about levels that are higher than what the background level should be. Basically, human activities have caused nitrate levels to increase. So if we take a look at this publication for a few moments, and I'd like you to read it over. If you happen to live in a geographic area where you're in one of these nitrate areas of concern, it may eventually impact your business operations. Because one of the goals of state governments throughout the country is to prevent nitrate levels in groundwater from reaching a level that would be hazardous to human health. The reason why I picked nitrate as my example of a groundwater contaminant for these series of lectures is that nitrates are very mobile. Remember, they're negatively charged. They sit in the water in the soils and they move with the water. There's nothing in the soils except for plant roots themselves that actually attract nitrates and suck them up. So nitrates are about the most vulnerable, or are about the chemical that's most likely to reach the groundwater. So we say nitrates are an indicator of groundwater contamination. If you test your groundwater for contaminants, if you find nitrates, you probably ought to look for other contaminants. If you don't find nitrates, your groundwater is probably in pretty good shape. And that's simply because nitrates are an indicator. If you find nitrates, then you probably should look for other chemicals in your groundwater. And we say it's an indicator chemical for several reasons. First of all, it's the most leachable chemical in the soil. So if something's going to get to groundwater, it's going to be nitrate because it moves very easily, and we use a lot of nitrogen fertilizers. The other reason why it's a good indicator is because it's relatively easy for us to determine nitrate levels in groundwater. It's cheap to detect. An analytical laboratory would probably charge you a minimum of $10 to $12 per sample, which is a relatively reasonable cost. For instance, if we were looking for a particular pesticide in groundwater, the analysis for that pesticide would range anywhere from $100 to $300 per sample. So you can do a lot of nitrate samples compared to other contaminants. And because nitrate is relatively cheap to look at in groundwater and everybody does it, we have a really large database. And that database contributed to putting together this nitrate area of concern database in Idaho. If we look at other contaminants, let's stay in the agricultural chemicals area for just a moment. Pesticides. Pesticides are expensive to detect. You're going to pay a minimum of $125 to $175 per sample. And in irrigated areas of the Pacific Northwest, because there's so much crop diversity, there might be 80 different pesticides that are commonly used in that geographic area. So if you're going to spend $150 per sample per pesticide and you've got 80 pesticides, you're talking about a huge amount of money. Conversely, if you're looking at nitrate as an indicator, you're talking about $10 to $12 per sample. If nitrate's there, then that's when we probably start looking for the most leachable pesticides. If nitrate's not there, the odds are that your groundwater's in pretty good shape. Okay, if we take a look at the background of nitrates in human health, the only reason we're concerned about nitrates in groundwater is that we drink most of our water in Idaho that we use for drinking as groundwater. 95% of the people in Idaho use groundwater as their source of drinking water. And high levels of nitrates can have an impact on human health. So let's take a look at these health concerns very quickly. First of all, humans ingest nitrates in food and water all the time. We have certain plant materials that healthy adults eat that contain 1,000 parts per million nitrate nitrogen. Huge numbers. But a healthy human adult can consume food that's high in nitrates, and these nitrates are absorbed out of our digestive tract, and they're excreted in our urine pretty fast. So studies have shown that nitrates really have no short-term impact on human adults. So human adults can consume fairly large amounts of nitrates. And again, very few short-term effects have been observed with large nitrate consumption. The one thing that I have to say is we don't really know what the long-term effects are of consuming food with high levels of nitrates. That's out, and there's really no studies to really look at the long-term impacts of consuming high levels of nitrates by human adults. However, infants have problems with high levels of nitrates. We know that children less than 6 months old are susceptible to nitrate poisoning. So we have a health standard for nitrates because we're worried about kids that are 6 months old or less. And this is what happens to a child that's very young. A child less than 6 months old consumes nitrate. That nitrate goes to the digestive tract. And when a child is born, our stomach decomposes the food that we eat using bacteria. It isn't until we're 6 months old that we have enough stomach acids where acids take over and do the digestive process. So when an infant is young, they consume nitrates, and bacteria in the digestive tract convert those nitrates to nitrites. Nitrites are toxic. Now remember, this goes away when the acids take over and start doing the digestion in our stomachs. And that child has to reach about 6 months old for that to occur. So these nitrates that are formed in the digestive tract, basically what happens, the nitrates enter the bloodstream and they react and combine with hemoglobin, which is our red blood cells. And when they react with hemoglobin, we form a compound called methemoglobin. And methemoglobin is a problem because it interferes with the blood's ability to carry oxygen. And of course, everybody needs oxygen. When a significant portion of the hemoglobin in an infant's body has been converted to methemoglobin because of large amounts of nitrites, the child takes on some symptoms. We call it blue baby syndrome. And blue baby syndrome is simply, you can look at a child's head and you see a bluish skin color. And this bluish skin color appears especially around the eyes and the mouth of the infant. Now this is a serious condition because death can occur when 70% of the hemoglobin in the blood supply has been converted to methemoglobin. In reality, because we recognize that nitrates are a problem, deaths are actually pretty rare. Okay, if you're an adult or you're over 6 months old, you don't have to worry about nitrites and methemoglobin. But if you're an infant, high nitrates could be toxic. Because of that, we have a drinking water standard that the Environmental Protection Agency has established. We have a drinking water standard of 10 parts per million nitrate nitrogen, which is equivalent to 44 parts per million nitrate by itself. But So drinking water should contain no more than 10 parts per million nitrate nitrogen for it to be safe for infants. Nitrates may also be problems because they react with organic compounds, which we call secondary amines, to form nitrosamines, which have been known to cause cancer. However, very little documentation on that. So again, we have a standard, 10 parts per million nitrate nitrogen. Things are almost always reported as nitrate nitrogen. Occasionally, you'll see somebody report nitrates as 44 parts per million nitrate, but that's the equivalent of 10 parts per million nitrate nitrogen. Now, EPA did research to establish a standard of 10 parts per million. All of our standards for drinking water are based on scientific research. Basically, what happens is the Environmental Protection Agency goes out there and does research. And in this case, they found that nitrate nitrogen concentrations of 20 parts per million or more in water may cause blue baby syndrome. It may be toxic to infants. So EPA's research said 20 parts per million. Then EPA comes in and they have that number. They have it, half it from 20 parts per million to 10 parts per million, and that becomes our standard. So we have guidelines for nitrate nitrogen right now in drinking water. And the guidelines are pretty simple and straightforward. If the nitrate nitrogen concentration of drinking water is from 0 to 10, it's considered safe for humans and livestock. Young cattle have the same thing in their digestive tracts. They start out with bacteria that digest their food, and by the time they're 5, 6, 7 months old, that bacteria has been replaced by acid. So young livestock is also susceptible to this. EPA guidelines are if the nitrate nitrogen in the water you drink contains between 11 and 20 parts per million nitrate nitrogen, that water is considered safe for human adults and for livestock, but you shouldn't use it for infants. You should use a different water source for infants because you could end up with blue baby syndrome if the infant consumed a lot of water. We also have other values in the guidelines. If the nitrate nitrogen values are between 21 to 40 parts per million, short-term use is considered okay for human adults. It's okay for all livestock, unless the livestock also receive a feed source that's very high in nitrates. This is considered to be risky for long-term use. You don't want to do this long-term. If the nitrate nitrogen levels are 41 to 100 parts per million, it's considered high risk for human adults to drink it. You shouldn't use it. You're not going to find wells very often that have that much nitrate nitrogen. And then finally, if the nitrate nitrogen content is over 100 parts per million in the water supply, you're not supposed to use it for anything. Basically, you have a liquid fertilizer here. So this lecture just kind of summarizes why nitrate is a hazard. It's only a hazard at high levels for infants, children less than 6 months old. It's not considered to be a hazard for human adults. I gave you some nitrate standards, 0 to 10 parts per million, what 20 parts per million is, what 40 parts per million. In the next lecture, we'll actually look at what is the likelihood that your water from your well will have high nitrates. We'll take a look at some data that was collected here in the Pacific Northwest. Thank you for your attention. And again, our next lecture will continue our discussion on nitrate and nitrate areas of concern in Idaho. Thank you. Productive from a nitrogen fixing basis. Alfalfa can fix or add up to 300 pounds of nitrogen per acre per year to the soil. Now, as long as the alfalfa plants are using that nitrogen for growth, it's great. But when we plow a field out from alfalfa, or when the alfalfa dies, some of that nitrogen can leak into the environment, become nitrate, and eventually end up in the groundwater.